Sorry. All right. So, yeah, welcome to session number 1, 5G solutions and experimentation for advanced industry. The first speaker is from Glanbia, so Michael. I hope you are online. I see you now. That's very good.
Can
so
hear you, Håkon.
Hopefully audio now is working, and we can switch to your presentation because you have your presentation on your side, right?
Hopefully this will work. Yeah, sure.
Yeah, it's working. Yeah, good.
So, okay to go, Håkon.
So let me see. Do I try to share in Teams? Are you able to? Are you sharing now in Teams?
No, I can start sharing now if you're ready. If we're all set up.
Yeah.
Okay.
Please.
Good.
Yeah.
Okay. Can you just confirm that you are seeing my output?
Yeah.
Okay, I'm going to go off camera now because it's easier to run through the slides off camera. So I'll just take you through the presentation. So I'm Michael Power. Thanks, Håkon, and thanks, Andrea, for the introduction. Okay, it's better. As Andrea has already explained the background to the project, Horizon project and program, I won't go into great detail about the background, but within the program, the 5G Solutions project was tasked with examining the potential of 5G technologies across a number of industry and media verticals, as Andrea has pointed out. In the industry case, the idea is that 5G and the cellular technologies that follow will be central to providing the characteristics of high reliability, low latency, and massive bandwidth that will be demanded of the factory applications of the future. As this is an attempt to investigate the real-world viability of these technologies, the method of experimentation chosen was to work with the partners who would actually use these technologies and then to actually deploy them in real-world industry environments in order to better understand the potential challenges that would be met and the benefits that would accrue following successful deployments. So Orbis and Glanbia collaborated on the 5G use cases for non-time critical applications as part of Living Lab 1. Orbis and Glanbia have worked together for many years deploying and developing manufacturing intelligence systems at many Glanbia facilities. So the use cases, how did we decide on the initial use cases? Well, we organized a series of workshops with key plant stakeholders, and we asked them to think about how a high-performing, reliable wireless communications infrastructure would improve plant operations. And we set some key selection criteria for the tests. This was all back in 2019 when the project started, an era pre-COVID. So what do we do? What's our function within Glanbia? We look after the global manufacturing execution systems that are used. They're kind of a layer between the manufacturing and our ERP or intelligence layer. So we have well-established manufacturing execution systems in Glanbia which collect and consolidate data from multiple sources, including the PLCs and distributed control systems that run our plants, from the SRP and ERP platforms that perform our enterprise applications, and the systems from a variety of other sources. And we use these data sources to form a contextualized view of the plant. The data models we construct from these sources are quite complex and guide daily plant operations in near real time. The outputs from the existing MES systems provide a range of plant visualizations, from operational reporting for hour by hour, shift by shift, day by day, paperless plant modules to minimize manual data recording, and a range of KPIs can be used to measure and trend plant performance over the longer run. We have been doing this for a long time, and we have achieved most of this using primarily wired technologies. The majority of the plant information is gathered from the programmable logical controllers, as I said. And while this information allows the MES platforms to construct a wireframe digital twin of the running plant in near real time, it has some gaps. Our ambition for our living lab was to address these gaps using wireless technologies. The benefits of the more complex data model I've described can also be leveraged by workforce mobilization. We included as part of the Living Lab the dissemination, consumption and augmentation of this data model by plant workers operating in the 5G wireless zone. This aspect of the experiment actually provided for us the richest learnings. So, what were our problem statements? This is what we came up with out of our workshops with the various plant stakeholders, and the key use cases really came up from our maintenance department. These were this is what we decided on. Really, at a high level, it was one about additional data collection methods from the running plant using IIoT methods to bypass or circumvent the manufacturing, the OPC layer that we were the traditional route for getting time series data out of the plant. And the problem statement 2 was about using this data and pushing this information back down to a plant operator who might be working in the plant space. So before we get into the actual test methodology and execution, let's first briefly look at the enterprise architecture and the 5G services that needed to operate in it. Glanbia is quite a large multinational organization and has well-established networking and security standards. We run a single SAP instance, and in recent years with a cloud-first technology, more and more of our enterprise applications are migrating towards cloud service providers. Our data-intensive manufacturing layer, however, is pretty much anchored to the plant. Integrating the 5G test lab into this environment presented some challenges, but these were compounded by the physical access restrictions to the manufacturing facility during the whole COVID-19 pandemic. As there were very few mature 5G offerings from the operators back in 2019 when the project started, our Living Lab planned to use experimental 5G private node running all the required 5G services as software modules on a commercial off-the-shelf hardware. The project was organized around 3 test cycles. Firstly, to align with the evolving capabilities of the 5G standards, and secondly, it allows us to adapt and learn from cycle to cycle and focus on the most valuable lessons along the way. From the very outset, we also made some key industry partners aware of our involvement in the project, and among these were our mobile network provider, Tree Ireland, and Irish Manufacturing Research Organisation. These in particular proved very important allies on our journey, helping us to understand the technologies and to integrate them, I suppose, in our plant. In the first cycle, Orbis established the technical landscape off-site and began working on a mobile app that would test the mobile maintenance or connected worker application. The intention was to use the private 5G service to automate the current process by allowing Craftworker to interact with new internal MES services hosted locally on the same LAN, on the same physical site. Excuse me. And this would have replaced the manual processes that preceded it, whereby the operative or craft worker would manually record operations or work programs at the site of the job, take these back to an office and transcribe them to a spreadsheet and for subsequent uploading to SAP before they would become available for reporting or analysis. So in cycle 1, we had already established the 5G node. We had already established a pilot app running on our mobile connected applications in a trial factory space, connecting internally across the various network components to our MES services, but in a test lab environment. In cycle 2, we moved the test bed to the physical factory at Ballyragget. And maybe this is the right time to take you inside the plant to understand the nature and scale of the environment and to give a flavor of the type of connected worker opportunities we explored. I'm just going to play a short video, and I hope this plays across the network okay. Maybe you give me some feedback if it doesn't.
Here at the Tirlawn manufacturing site, we were given the opportunity to investigate the potential of 5G technology as part of Factory of the Future, an EU-funded Horizon 2020 innovation project. As it stands, our site at Ballyragget, County Kilkenny, is one of the biggest dairy processing facilities in Europe, processing 1.3 billion litres of milk per year, and which comprises of 36 highly automated plants, with hundreds of kilometres of pipework and cables, and 27,000 individual pieces of equipment. However, if we were to start all over, one of the things all workers would want is connection in real time to all areas of the facility. The ability to interact with every piece of the equipment. Using a maintenance Neptune app on their handheld device, the connected worker could access every asset through individual QR codes, giving them the ability to complete administration in real time, with better records that include pre-work and post-work photos, access to previous works, and SOPs or specification. Parts could be booked, costs generated, and precise records of works captured, all of which would enhance efficiency and food safety. Called Everywhere Connectivity, this is cutting-edge manufacturing technology. This is the future of Tirlawn.
So during cycle 2, it became very obvious that while we had successfully established a mobile connection over a private 5G node installed in our plant to a local IT service, also in our plant, we would need to extend the coverage to more of the plant assets, and we would need to bypass the local middleware application to optimize or maximize the use of the 5G applications. As I said, we are moving towards cloud services, and our entire maintenance operation is delivered from SAP services in the data center. So 3 Mobile worked with us to extend the coverage from their public 5G offering inside the Ballyragget plant using an Ericsson indoor 5G radio lab solution. And our internal applications team used our SAP Neptune platform to extend or expose the maintenance functionality we needed. This is what you have just seen demonstrated in the short video. So what did we achieve? A functional test of the private 5G technology in the use case was successful, and for the purposes of the project, we managed to create a secure 5G service, private 5G service inside the plant and integrated with the existing enterprise architecture. And we created an outbound KPI connection for open source connection to share the results of the experiments with the project platform. The limited coverage of the experimental private node narrowed the scope of what we could achieve, however, and some of the metrics you would expect from a 5G installation were not met. However, from a user experience point of view, what we learned is that both the private and the public installations provided a satisfactory user experience for our non-real-time requirement. So our involvement has created an appetite in the organization for more connected applications, and I'd say we've created a lot of excitement around the organization. And from an enterprise network roadmap planning point of view, we can see that cellular network services are likely to take a far more central role in the next generation of enterprise network strategies. So what's the vision for the development of our use case? Well, we can see that retaining the manual plant processes of the past is difficult to align with the widespread use of powerful computing endpoints now available to everyone. We have demonstrated possible first steps in focusing on digitizing maintenance operations in the working plant. And it's not hard to imagine a further enhancement of those by more sophisticated wearables running more advanced applications at the network edge. Our involvement in the project has created an appetite in the organization for more connected applications, and we have shown that we can start to deliver these almost immediately. So finally, in an effort to understand where the organisation was positioned on its Industry 4 journey and where the next investments should be made, in order to maximise return on the IMR introduced us to the SIRI framework. SIRI is the Smart Industry Readiness Index, and SIRI is a global recognised suite of frameworks and tools to help manufacturers, regardless of size and industry, start and scale and sustain their manufacturing transformation journeys. And while we're very pleased to score at the top, among the top of our peers, areas for focus for us included vertical integration, shop floor intelligence, and workforce learning. And in the enabling technologies to move us along this roadmap included wireless evaluations, OT layer investigations, and API platform integration. So does 5G have a role in enabling these technologies have advantages in leveraging these technologies over Wi-Fi or legacy cellular applications? So we have learned a lot about 5G and we've understood the non-real-time demands of our use case, have not stressed its capability fully. We've learned about the paradigm shift in the move from 4G to 5G and the softwarization of network services. We understand the promises of network function virtualization, slicing and network orchestration and a future application landscape characterized by containerization and suitability of 5G architecture to deliver low-level edge compute. We have yet to establish if it's the best option to support our smart industry journey, but it's certainly a candidate for future investigation. This has been a very high-level whistle-stop tour of our living lab involvement. Exciting times ahead for sure. I could go on, but I think I've used up my time slot at this point. So thanks for your time and attention, and thanks to Akon, Andrea, and Albert, and the project leadership team for your constant support and guidance. And with that, I will hand it back to the room. Not hearing you, Akon.
Okay. Right now.
Was I unmuted now? Can you hear me now?
Yes, we can hear you now, Akon.
Okay.
I think.
*6 command.
Right.
The month's number.
Let me see now. Yeah, maybe we do have time for a quick question. So Michael, I was, we have this KPI visualization system in the project, which is sort of very focused on 5G connectivity. I was just thinking of your needs in terms of widening a scope of a visualization system, more from a dashboard point of view, meeting your industry needs. And any comments on this? So thinking ahead, for future opportunities.
I'm not sure. I'm not sure. We have very mature visualization systems already in place for plant data. I think if it's an attempt to say that we have open source platforms available for taking existing plant data and representing them as a managed service. Yeah, possibly, but you're in a very competitive marketplace if that's what you're targeting. There are many industry players providing legacy servers, maybe not open source, but legacy applications in that. There, I can think of Rockwell and PTC and many other application vendors in the manufacturing space with years of experience delivering solutions like that. I think the focus might be, or a better angle to collaborate might be, to provide the mechanism for us to reduce our plant footprints. Our MES applications are very heavy in the plant. They have a lot of data transferring from our physical plant to our local time series historians, and the challenge is to reduce those flat plant footprints in favor of cloud-based services, or certainly data center services. And I think a better opportunity for the mobile operators might be to provide the edge compute capability to allow us to shift that compute away from the plant and towards the cloud. So, and that would be playing, I think, more into the core strengths of the telecom operators, rather than competing with people who are already expert in the data visualization area. Don't know if that answers your question, or if you've even heard the right question. I think
maybe even providing an even wider perspective on this, but I'll take your comment. Think about it maybe for the panel. I think the next speaker up is Silvia Canale, representing RS2T. Maybe Silvia, you can introduce yourself more. The presentation now is shifting a little bit to smart energy, but Silvia, please, the floor is yours.
Yes, thank you, Håkon. Good morning, everybody. I hope you can see my screen. Can you please confirm me from the hall?
Not yet.
Not yet. Let me see.
I think now it's coming, yes. Now it's good.
Okay. Thank you so much. So welcome, everybody. It's a very honor to me to be here remotely, unfortunately, to manage this session about the 5G technologies for smart energy services, supported by the large industries taking part in our Living Lab Smart Energy, IREN, and NLXWay. During this presentation, I would like to give you an overview of the 3 use cases that we are developing in the 5G Solutions project. After reviewing the key partners and the objectives in our Living Lab, I will show you the main KPIs collected and the rationale behind the 3 use cases, the industrial demand-side management one, and electric vehicle smart charging, strictly connected to the third very challenging use case, namely the electricity network frequency regulation. And we will flow at the end of this presentation to an open discussion with my colleagues from the IREN Group and NLXWay. Key partners, so as Andrea presented before, 5G Solutions is a big research project combining different facilities in different countries and 4 living labs. Our living lab is participated by 3 large industries. The first one is IREN Innovation from the IREN Group, a multi-utility operating in the most of regions in Italy, and is a vertical partner for 2 use cases, the demand-side management one and the smart charging, electric vehicle smart charging one. The second one is the NLXWay from the NL Group, worldwide leader in electricity and in electric mobility. It was the vertical partner involved in the frequency regulation use case, as well as the electricity vehicle smart charging. RS2Team Company is the technological and business coordinator of the Living Lab. They developed from the technological point of view the 3 smart energy services, supported by the Consortium for the Research in Automation and Telecommunication, namely CRAT, including high-profile universities and academic profiles in Italy. In particular, we worked with the group from La Sapienza, University of Rome. And of course, TEAM, not only has enabler, has the operator supporting our 3 use cases, but also as technological partner participating in the co-creation of our smart energy services. The Living Lab was based in Italy, and the main objective was to validate 5G technologies as key innovation factors for the forthcoming decade will be significant in the energy sector, identifying and meeting the business-oriented KPIs to develop go-to-market services with additional value with respect to the present one, and introduce new requirements and control-based optimization strategies very useful in vertical domains, such demand-side management in the energy market, and of course evaluating the business impact of these solutions. So our Living Lab was based in the city of Turin and includes 3 use cases developed in 3 trials cycles. The first one dedicated to the development of the single components, the second one devoted to the integration of the components, and the third one that is currently ongoing, dedicated to bringing the solutions to a TRL up to 7, so demonstrating in industry relevant scenarios. We used up to 6 5G devices simultaneously in one 5G platform provided by the ICT 17 project 5G Eve, providing the necessary extension operated by TEAM, the coordinator of 5G Eve and partner and coordinator in 5G Solutions project, to support our 3 use cases. In the small map of the city of Turin, you can see the several sites managed and made available by Iran Group and Enel Group. Why smart energy services? Nowadays, heterogeneous energy sources and the introduction of concept as the active demand prosumer and the energy community, as well as the pervasive diffusion of the electric vehicle spread out especially in the urban area, are requiring for a 5G communication guarantee high reliability, low latency, and high and wide coverage in terms of device density. So the main focus in 5G solutions and our Living Lab Smart Energies was dedicated to scheduling and dynamic aggregation of energy loads, supporting the restore of the balance in order to reduce the discrepancies between the supply and demand, resulting in sometimes grid frequency beyond the nominal bandwidth, providing outages and interruptions. All that by remotely controlling and modulating the smart charging process. So these focuses are served by 5G powered control and optimization distributed framework that was realized and validated in the 3 cycles of trials in the 5G Solutions project. The first use case owned by the Iran Innovation Company from the Iran Group focused on industrial demand side management. So in this case, the energy load scheduling and dynamic aggregation, control, and heat pump provided in a building. Why a heat pump? Because nowadays the renewable energy sources supplies is intrinsically intermittent, causing this unbalancing, unavoidable unbalancing in the electricity grid. And this is source of power outages and blackouts, frequent blackouts. So distribution and transmission system operators are seeking solutions for flexible management of the grid by means of dynamic regulation of loads. What kind of loads? Electrical heat pumps, shiftable appliances in domestic and residential environment, as well as electric vehicle chargers are considered the most significant systems to be used as flexible load if properly controlled. These loads are managed according to the availability of a power supply and, of course, the need for a remote distributed control system for energy load shifting disconnection during the operational tasks. So we demonstrate the use case by two test cases. The former focusing on the remote controller of the heat pump. So in this case, the heat pump is controlled by a remote monitoring control unit provided by 5G devices, and is very quickly and reliable connected to an experiment server hosting the local controller, the remote and local controller. So in this case, you can see on the left the building heating distribution system using fan coils and low temperature radiant floors with the renovated energy production plant, so a last generation plant, with the heat pump in the picture beside, with the remote monitoring and control unit connected by 5G to the experiment server, and the remote controller is hosted in the experiment server. In this test case, we were very careful to the KPIs in terms of actuation time, so the runtime time, communication, and service actuation time, where the average we registered was about up to 200 milliseconds. It was quite suitable to support the remote control of the heat pump, with minimum values around 75 milliseconds. In the second test case, we tested the reactive load disconnection for blackout avoidance. So in this case, RS2T developed a local controller in terms of POC, TRL5, with a remote controller controlling the appliances in a domestic environment. Even in this case, the KPIs were very important in terms of disconnection time, composed by the sensor update time, the data processing time, the remote controller update time, and of course the actuation time, where, as you can see, the sensor update time and the actuation times plays the most important role in the disconnection time. And we registered that 5G communication time impacts less than about 10%. On the opposite side, the 4G communication in comparison impacts more than 15%. So this is something that opened the way to the development of remote control system based on 5G communication. In the electric vehicle smart charging, both Even and Enalex Way provided their facilities to test an innovative smart charging framework solution. Why smart charging? Because this program allows the electric vehicles to participate actively in demand side management market. In particular, the real-time power set point needed for smart charging are computed by solving a quadratic optimization problem based on the model predictive control framework, very known to solve the complex optimal control problem. In this case, we take into account the driver constraints as well as the transmission in the distribution system operator constraints in terms of load curve, target load curve. Unfortunately, as the number of the electric vehicle increases, the complexity of the optimization software to be solved may explode. So the centralized approach doesn't scale very well with the number of chargers that is even more and more present in current load areas. And we had decided for a decentralized approach requiring, of course, the composition strategies from mathematical optimization and operations research, but also distributed resource management allowed by 5G communication. In fact, in this case, reliability, low latency communication among many agents able to decompose the optimization problem is fundamental to reduce the overall computational time and to reduce the control sampling time in the smart charging operation. Here you can see the first deployment architecture we developed in the cycle 2 in the ERN facility, where the charging point operator is connected by the Teltonica router to the local control agents. You can see in the middle of this architecture, and the master control agent on the left, on the right, is in charge for the control in optimization algorithms. In this case, the main KPIs were, of course, the sampling time that we, in this use case, we we kept less than 5 minutes. That was very good in smart charging, but it can be reduced up to 1 minute. And the vertical service communication times plays the most important role. And we registered the mean service communication time less than 100 milliseconds. That was quite good. The network KPIs in terms of latency, availability, reliability are suitable to support smart charging in this scenario. And on the right, you can see has 2 chargers charging 2 distinct vehicles, can represent 2 loads that can be aggregated in order to follow the red line consisting in the optimal target load curve decided by the charging point operator. The third and final use case is the one devoted to electricity network frequency regulation. In this case, the vertical owner of the use case is NLX-Way. The participation in frequency regulation services nowadays is limited, of course, to the production units with strict specifications in terms of capacity, reaction speed, and other important variables. And the aggregation of many electric vehicles might meet requirements and contribute to the primary frequency regulation services. This use case is very experimental, and so it was considered the most ambitious use case in our living lab. The solution developed by the UC owner is charging the electric vehicles in order to participate to the frequency regulation services with strict activation times, less than 300 milliseconds. So with respect to a solution that is too expensive, equivalent to equip each charging station with 1 frequency meter, 5G allows to distribute the communication effort and the calculation effort by keeping just 1 load area with the frequency meter and to share the values registered by the frequency meter among all the charging stations. During the cycle 2, so not yet in industrially relevant scenario, that is the one we are testing in cycle 3 in these days, we set up a frequency measurement and communication framework to be tested in cycle 2. So in this case, the frequency meter was not yet integrated in the charger. That is the one we are realizing with NLX-Way during cycle 3. And in lab, we tested the test case for the communication aspect. And as you can see, the reaction time was kept to meet the strict requirements in frequency regulation, so less than 300 milliseconds. And the vertical service communication times was considered suitable to allow the on-the-field test case execution that we are performing in cycle 3. That was a very nice results we obtained in cycle 2. This was a very brief presentation of our 3 use cases. Now I would like to give the floor to my colleagues from the EN group and the NL group, Ilaria Vigna and Maria Chiara Cavarretta, to answer your questions or curiosity, or if you need additional information about our results, we will be very pleased to answer. Thank you.
All right, thanks a lot to Silvia and the team that have provided a very nice presentation overlooking many topics in the smart energy area. So any comments, questions from the audience here? And Silvia, you can hear me now, right? I don't need to have the *6, right?
I can hear you very well, thanks.
That's good, yeah. So I think, for the benefit of timing here, I think we should move on to the next presentation, because the next presentation will be on site. So I'm happy to welcome Anna. Yeah, we will then disconnect from here. Back to your laptop. You need a pointer. So We take the benefit of inviting other projects here. So Anna is representing 5G Victory, and you can provide a little bit more. Hopefully that Norway is working fine for us. Yeah, that's it. Well, and I guess 5G Victory is also an ICT-19 project, right? So we are sort of sister projects in that. Okay. So sharing code. Yeah, looks like this. Very good.
Okay. Good morning. My name is Tzanakaki. I'm an associate professor at the National Catholic University of Athens in Greece, and I'm the technical coordinator of 5G Victory. I would like to thank Andrea and Falcon for giving me the opportunity to be here today. It's really good to be back and meeting you. And I will try to give you some insight on some of the work we do in 5G Victory relating to Industry 4.0 services. So as you say, the two projects are ICT-19 projects, so they're sister projects. And there are some activities that are quite similar. Okay, so as this is a project that maybe some of you are not familiar with, I will take the opportunity to say a little bit about the project. So the overview of my presentation is as follows. The pointer doesn't work on the screen. Oh, no. Okay. Okay, no worries. Okay, so I'll start with the 5G Victory overview. I will say a little bit about the overall architecture in order to introduce the topic of the presentation, which is AI-assisted Industry 4.0 services over a 5G platform. Specifically today, I will talk about a railway use case. So I will give you some insight on a specific railway use case we have been working on. There are a lot of activities in the project, but I picked up just one example that I think is relevant to this workshop. And then I will say a little bit about how the nature of the service affects our underlying 5G infrastructure and how we can optimize our network to support Industry 4.0 services, and then try to give you a summary of the lesson learned through this particular use case. Okay, 5G Victory in a nutshell. I already introduced the project as an ICT-19 project. The acronym stands for Vertical Demos over Common Large-Scale Field Trials for Rail, Energy and Media Industries. The project had originally a 3 years duration. We granted an extension of 13 months, so we're finishing this summer a little bit later than you. The budget was of the order of 13.5 million, and it is a consortium of 26 partners that are across 8 countries, and of course it's a consortium of both industrial and academic partners. Okay, some key objectives. The central vision of 5G Victory was to design and prototype an open 5G infrastructure which is capable to instantiate and co-host various vertical sectors. We very, very seriously looked into the integration of commercially relevant and operational environments in order to support demonstration of vertical use cases over the 5G Victory, the 5G infrastructure that 5G Victory developed. And the big vision was to transform existing, closed, purposely developed and dedicated infrastructures into open environments. The 5G Victory exploits, as also you do, some of the ICT-17 infrastructure. In fact, it brings together all ICT-17 infrastructure. So we have presence through 5G Vini at the Patras site. 5 Genesis, we have the Berlin site. 5GE, we have the French-Romania cluster participating to the project, and we're also integrating the 5G UK testbed in one pan-European network infrastructure. And the vertical use cases we work on focus on transportation, energy, media, and factories of the future. I mentioned that the vision of the project was to create this open infrastructure, and the means towards this direction was to expose resources and functions through common repositories. So through these common repositories, this type of resources and function can be accessed and shared on demand to support efficient and flexible service provisioning. In addition to this, 5G Victory is developing an open data management platform for scalable data collection and processing, machine learning and artificial intelligence techniques for optimized services. And this is probably the part that I will focus more today. Okay, so here, unfortunately, my pointer doesn't work. I try to give you a high-level view of the different deployment options that 5G Victory architecture can support. We're able to support, from an architecture perspective, both public and private 5G services. So we have isolated private network, 5G network capabilities as well as public. In terms of RAN, we have full capability spanning from the monolithic 5G RAN solution to a fully disaggregated solution where the RUs, DUs, and CUs can be located between them. And the key role in this plays the transport network, which is a multi-technology transport network combining wireless millimeter wave type of solutions with optical network and Ethernet. Okay, the overall architecture involves the element I described before. Of course, we have at the very bottom of you can see the different domains. You can see the RAN with the MEC capabilities. You can see the core. You can see the transport network that supports connectivity between the different elements. But of course, this is a multi-layer architecture. So at the very bottom, you see the data plane. On top of this, a control plane. And per domain, you can see the different orchestrators. Now, for this to work as an integrated infrastructure, we have a management plane, which offers distributed control plane operations empowered by an intelligent plane. And this intelligence plane involves several elements in which AI modules play a key role. Of course, AI modules are implemented at different stages and different layers of the architecture I'm showing you here. I don't want to take too long on this, but I will just highlight the fact that the machine learning is a key aspect of the intelligent management and control plane. We have several building blocks involved, and these need to interact. And of course, this requires appropriate interfaces, vertical and horizontal. And if we try to identify the main components, we have a machine learning pipeline subsystem, which comprises a set of nodes. Each one of these have specific functionalities, and then we can create machine learning applications by combining these functionalities appropriately. And of course, for this combination to operate, we need an orchestrator. So we have the ML function orchestrator that you can see at the very middle box of this diagram that manages and orchestrates all the ML nodes and respect constraints associated with ML intent or network level constraints. Right, to move on to the Industry 4.0 use case, I'll try to show you a specific use case that we worked on and implemented as part of our 5G Victory activities. From the very beginning, I introduced the fact that this will be a railway-related use case. So what we have done is we worked trying to give a solution for an automated system that detects track defects in railways. So basically what we do is we monitor the tracks and we can identify anomalies, and through this we can identify where defects lie. This is a very serious problem for railways. And this is the implementation. This is just some photographs from the implementation work we've done. We used Tzanakaki as a partner that brings this use case in the 5G Victory consortium. So they provided a train in which we have installed a set of different sensors, and the train had a trip, and we gathered the measurements and evaluated the performance of our system. And specifically here, you can see the train, you can see the various sensors that we installed on the train, a vibration sensor, accelerometer, and we also installed an industrial camera at the front of the train that was actually monitor the track itself as the train was moving over. So we deployed a measurement platform that can be used to estimate track irregularities, anomalies. This platform takes measurements from the multiple sensors I described, and these are processed in order to, through AI models, in order to identify anomalies. And what we find through the measurements of the sensors, we compare with what with the video we record from the industrial camera. Okay, just to give you an idea of how this fits in the pipeline idea I was describing before, we have our onboard sensors, we collect the data, so we have the data onboarding, so real-time collection of field measurements. Then at the edge, we perform descriptive analytics, so the AI models identify anomalies, and on the top diagram, you can see the red dots. This is, in fact, the path the train follows, and where the red dots are the anomalies. So we identify defects across the rail track. Then we do predictive analytics. So we use this data in order to be able to predict anomalies and possible failures in the track. And finally, we do perspective analytics in a central domain where we actually process this data and we identify strategies to react. So basically, if we see that there's a failure here, terminate the service, send somebody to fix the problem, and so on and so forth, all in an automated fashion. And this is all supported through the architecture I described before. Okay, and here you see also the images from the camera. Obviously, I cannot show you real-time streaming, but we get the very, very high-resolution images of the camera, and then we have correlated the data that we have measured through the sensors with the image of the camera, and we can identify also the type of defect of the track. Now, the problem that is associated with the challenge associated with this approach is the fact that if we want to have good resolution and therefore good accuracy in what we do, we need to increase the sampling rate with which we send the data. So increased sampling rate will improve the accuracy of the ML models, and we will be much better in detecting track defects and predict future issues. Also, we have a camera, I said before, so increased image resolution would help in the process. But of course, this increased the load of the traffic in the network quite significantly. So what we have proposed is, okay, let's not do this all the time, but be able to do this adaptively. And when we find areas that are very, we identify defects, then we become a little bit more intrusive. Well, we get a little bit more insight. We collect a lot more data for these particular areas. But the problem is that this is directly reflected on the 5G services. So if you want to do that, that's very good. But then your 5G network has to adapt to this. And then the question is, how do you deal with this? We were able to deal with this through the ML function orchestrator I mentioned before, but this then has to communicate with the orchestrator that supports the 5G service. And this can happen, of course, because then this orchestrator can increase the network and compute resources to support the required services from a 5G perspective. Okay, here you can see the dashboard. You briefly mentioned the need for a dashboard. We have developed a dashboard. Here you can see on your right-hand side, you see the vibration level that we observe as the train moves across the tracks, and you can see there are points indicating there's an anomaly at that particular location. And then we can analyze this, and the vibration experts can get some more insight from spectral characteristics of the measurement, and this is what you see on the left-hand side, but of course it goes well beyond my field of expertise. The capability that the tool we have developed, the platform we have developed, gives us the ability to pick different neural network configurations, and depending on the neural network we choose, then we can get different level of accuracy and prediction of our data. Okay, of course, the whole story, I think, is quite clear, but it has an impact on the 5G network. And the first part of the work we performed in the field, the second part of the work we performed in the lab, because we try to see the impact that this kind of service will have on the 5G network. And we try to understand this in a real environment, in a deployed platform, but in the lab, not in the field at this point. Okay, so the network scenario we looked at is having a hierarchical optical transport network that interconnects 5G RAN and 5G core elements. We have, you see the track here. Sorry, my pointer doesn't work. You see the track here at the RAN, right? And this is the track across which the train moves. In specific regions that you see in a darker color there, we have identified areas of defects. So these are the areas that we would like to intensify the 5G service and offer more resources for the service to be supported. And we assume to have we do have an end-to-end orchestrator that gives us real-time optimization of the whole system, again, using AI. So we use AI optimize the service of the Industry 4.0 service, but also to optimize 5G services. Okay, so here is a deployment that we have in the lab. We have a set of RUs, MEC and central cloud capabilities. We have a transport network, which is SDN controlled, and the different RUs here correspond to the different RUs I showed you before. So we have different sampling frequencies. So the input data have different data rates, basically corresponding to different sampling frequencies of the Industry 4.0 service. And at the right-hand side, you can see the equipment which we have used, the hardware which we have used to support the 5G platform we have in our lab. It's a standalone 5G platform based on open air interface, provided by Eurocom, a partner of our consortium. Okay, now the 5G side of things, AI 5G service provisioning, we again adopt a hierarchical machine learning pipeline to perform a set of operations. We do this in steps. We have step one. We deploy AI models at the edge, at the very bottom that you see on this graph. And we perform analytics at local level. So local analytics can help us with things like mobility prediction, prediction of network traffic. Then we move up. We deploy step two. We deploy AI models at central location. You see central cloud, second level up, to perform area-wide analytics. And then we can, for this, we use predictions from the local MEC, which you see at the bottom of this graph. So we can do things like backhaul traffic predictions. We can estimate the complex parameters associated with elements like, for example, the UPF. And then we have step three. We deploy AI models at the central controller where the orchestrator lies. And there we can perform end-to-end performance estimation. We can do end-to-end service optimization. So, for example, end-to-end energy-aware routing and things like that. Okay, in terms of, I don't know how well I'm doing with time.
5 more minutes.
Okay, in terms of the specific implementation in our lab, I'll show you some indicative results we have produced. For step one, we applied our local analytics. So it's MEC trains a set of AI models to estimate resource, energy, and other parameters. The AI model uses input measurements taken from the distributed base stations that you see at the bottom of the plot. And here you can see some of our results. For example, the level of accuracy is something we're interested in. In this plot, you see the loss function on the right-hand side, and this is inversely proportional to accuracy. So low loss means high accuracy. And what we see is that we get high accuracy when we consider a large number of base stations in our prediction. So the neighborhood that we take into consideration matters. Of course, this is something that one would expect. The problem is that you get this and you pay in complexity, so the training time increases. So this is a trade-off one can play with. And then you can see the right-hand side shows you, for example, resource blocks as a function of time. The measured data are indicated with the orange line, and the predicted data with the blue line. They have relatively good. They are in good agreement, and the gray shape here indicates the confidence interval, which is 95%. I showed you we can optimize our AI model to improve accuracy a little bit more, but this is just for you to get an indicative idea. And then we can do things like estimate complex functions, I said before. So, for example, we can use AI to predict power consumption of the overall system. And that's what example that we show you here. So here is the throughput versus time, the throughput of the system versus time. And you see the variations. And then the right-hand side show you power consumption again versus time, and the orange line indicates what was measured, and the blue line indicates what we estimated through the AI models. It's good agreement, and an interesting point to make is it's very hard to use, so far people were using cost models to estimate this kind of parameters like energy consumption. The problem is when you actually do this over this very, very complex systems, you can never do this accurately. So you can see that we have energy consumption in areas that we don't have traffic, right? And this is because of the complexity and the operation of the system. And if you use a typical analytical model, this would not be reflected. So it's very, very important to find optimal ways to evaluate the system. And then we go into the central analytics. So we gather the predictions for the local MECs I was explaining before to predict the status of centralized functions, like, for example, the UPF. And here we have estimated the total CPU waiting time at the UPF. So this is how traffic varies with time. And then the right-hand side diagram shows you the total CPU waiting time. Again, measured is orange, predicted is blue, good agreement between the two. And step 3, prescriptive analytics. So we transfer the trained ML models at the central cloud to perform system-level optimization under the realistic constraints that are associated with the system. And what I show you here is a specific example that we worked out in our lab, and is based on combining Gaussian process regression and Bayesian optimization. The technique doesn't matter so much, just indicatively to show what was implemented. So here, what we try to do is identify optimal power consumption strategies to use for the orchestrator to make decisions on which is the optimal path with regards to energy. With red here, we identified the optimal policy that we adopted. And when we adopted this policy here, you can see the results. Orange circles indicate total power consumption for different throughput when we apply static routing, and blue points indicate what we achieve when we apply the optimized strategy through AI, the AI approach we adopted. So basically, increased energy efficiency through this approach with really realistic estimation of what is happening in the network. Okay, so trying to respond to the question. Lessons learned. We have, through this work, we have seen, and then work that is happening across the consortium, also for other use cases, we have identified that Industry 4.0 services can be effectively supported, of course, through 5G, but also with the assistance of AI. We can optimize Industry 4.0 services, but when we do that, we directly impact the requirements these services bring from in a 5G context. And then we have found that we can bring additional degrees of intelligence in the 5G infrastructure and make it more suitable to handle the specific requirements that Industry 4.0 services bring. So this is, I think, everything from me.
Yep.
Thank you very much.
All right, thanks a lot. I think this is a really interesting scenario, mixing the sort of the industry side with the network side. Any questions from Orlando?
I have a short question. Usually in machine learning, one of the main challenges is data, availability of data. I'm not sure if you had this issue here, but can you give us, a brief impression on the availability of data?
You're absolutely right. So for this was a really a use case implemented in the field. So the data was real and it was collected through an operating train. So we deployed the sensors on the train. The partner that helps with provides the use case, it's Tzanakaki, the train rail operator in Greece. So we installed the sensors on the train. They gave us the capability to have a trip across the track. So these are real data coming from the field. In general, you're absolutely right. Now, for the 5G case, and this is really a problem that we have been facing as an academic organization. So a few years ago, we tried to do studies, and we never had access to any data. And this, so what you say, I totally know, and I totally agree. So the exercise we had to go through as a research lab was to deploy our own 5G platform. So we deployed the 5G platform based on OpenAI interface. It's another partner of 5G Victory. And the measurements I showed you for the 5G network are real data collected from the 5G platform. So you cannot find open access to 5G data. Now, we have some traffic statistics real traffic statistics for cities, for example, and we have Cosmote is a project partner for 5G Victory, and they have given us some traffic statistics, but these are not 5G, right? So these are older, few years ago statistics that we use in order to get an understanding as input to the platform to get an
train your models on it. So.
Yes, but what we say 5G data is data we collect for the platform. So we may import statistics from the city to the platform and then get 5G type of data. It's what you say is absolutely critical. So you can never really draw conclusions unless you have a solid idea of your data nature. So totally true. So for us, it was really an amazing opportunity to put our hands on this system.
Sensors generate lots of data. So,
yeah, but what do they reflect, this data? Yeah, absolutely.
How accurate can you kind of find the position of the damage, the location?
You mean how far?
Yeah, how many meters kind of
so in terms of accuracy?
Could you send kind of the repairman? How kind of accurate can you give that location?
Well, this really depends. I showed you these accuracy parameters, right? So it really depends on how well you can, how much data you have and how well you can train your models. We have accuracy levels of the order of 98%.
Meters.
Well, I think
easy it is after that to find the crack.
Okay, let me comment on this. I'm not sure I can give you a number, but I can give you an idea of the process. So what we do is we timestamp the data, and we also have a GPS, so we can correlate time and location, right? So we can. So this is actually quite good. It's not very far because this is something very important, right? So you identify your anomaly, and you can identify the location where the anomaly happened. And on top of, and this is for the sensor data. On top of this, we have the camera. So we correlate all three types of data, right? What has been measured, the location, plus what we get from the camera. So actually, it's quite good. I think, if I'm not mistaken, is of the order of, is not meters, is centimeters.
Short of time. Sorry for this. I think you should take it
offline.
Because otherwise we get into trouble with the audience. We have quite a good audience. So thanks a lot again. So just to let you know, I will stop recording now. We take a break. So I think we need the 15-minute break. Let's see now.